In this chapter, we discuss sound waves, like a sound wave that we see here. On the left side, we have the source of the sound wave. It's an oscillator in gray. That could be the cone of a speaker vibrating, hitting the air and creating a chain reaction that carries a sound wave. It could be our vocal cords vibrating. It could be a guitar or piano string that's vibrating, that's setting up the sound waves in the air. Notice that if you look at one air molecule, like the ones that are marked in red, they just move back and forth in simple harmonic motion. They have an equilibrium position, right about where I have the cursor. They have an equilibrium position and they just move left and right, back and forth around that equilibrium position. The air does not actually travel from the source to our ears. The air just vibrates back and forth. However, a chain reaction is set up that carries the wave along. So sound, like you know, is an example of a longitudinal wave. The actual displacements of the medium occur along the direction that the energy is traveling in. We, of course, want to contrast that with a transverse wave, where the simple harmonic motion is sideways or transverse from the direction that the wave is propagated. Notice that with a transverse wave, it is tension that is the mechanism which carries the wave along. When the medium is curved upwards, the tension from its neighbors pulls it down, and that carries the wave along. With a longitudinal wave, it is pressure which drives the wave. The speaker hits the air, that creates a high pressure zone which bombards its neighbor, and so on down the line. And that sets up a chain reaction of pressure wave that travels down. What I want you to again notice is there are two things that are happening here. One is there's the longitudinal motion of the air molecules, and number two, there is a pressure wave which is created. Here, this highlights the particle motion that creates the pressure wave that travels along, and we'll occasionally use some terminology. The compression zones are the places of high pressure. Rarefaction zones are the locations of low pressure. Notice that there is a pressure wave, in this case, a sinusoidal pressure wave, which moves along. There is atmospheric pressure, and the pressure of the sound wave rises above and below the atmospheric pressure. So we would call that P max, the amplitude of the sound wave. We'd measure P max as the amplitude of the sound wave. On the other hand, there's also the maximum displacement of the air molecules. So an important question to be able to answer is, if the speaker vibrates back and forth by some distance, and therefore the air molecules have a certain amplitude, what's the pressure amplitude which is created in that sound wave? So how is the sound wave displacement, the actual distance the air moves, related to the pressure that wave produces? What you do is you take the density of air, that's the ambient density of the air, multiplied by the speed of sound, which is about 343 meters per second, and you take that, multiply omega, that's the angular frequency of the sound, multiplied by S max. S max is the actual air displacement, the actual distance the air molecules shift in the sound wave. So to prove this would require like a separate lecture. I just want to argue the units make sense. It's supposed to be pressure. It's density times speed, and then omega S max is also a speed. You should recognize omega times amplitude as the peak speed in simple harmonic motion. So it's density times speed times speed. And you should remember from Bernoulli's principle, 1/2 density times speed squared it does have units of pressure. So this lets us figure out the pressure amplitude if you know the displacement, and vice versa. For example, the faintest sound like a whisper quiet sound, has a pressure amplitude of only about 10 to the minus 5 pascals. That's about the pressure of some super thin foil spread out over a square meter. Our ears can pick that up. Find the corresponding displacement amplitude. So when that whisper quiet sound is going through the air, how far is the air actually vibrating? So now we're solving for S max in this case. S max, it's the pressure amplitude, delta P max, divided by air density times the speed of sound times omega, which is 2 pi f. And it gives a displacement amplitude which is incredibly small. It's about 10 to the minus 11. It's 6.7 times 10 to the minus 11 meters. Incredibly small. An atom is only 10 to the minus 10 meters across. So in a whisper quiet sound, pressure is incredibly low, and the air molecules only shift a tiny, tiny fraction of their width during the sound wave. Incredible that our ears can even pick it up. Now, intensity of sound waves. First of all, what does intensity mean? Intensity is the concentration of the sound power. For instance, fireworks are loud, but if you go far away from them, they're not loud. The actual energy that comes out from the explosion is large, but how loud it is depends on how the energy has been spread out through the air as it travels further out. So intensity of sound waves is measured as watts per square meter. The concentration of the sound energy. It's an average of a sinusoidal wave, and we know that when you square an average, you get a half. So it's going to involve 1/2. And then you take delta P max, the pressure amplitude, and square it. As usual, the energy of a wave depends on the square of the amplitude. And you divide it by rho times V. If you want to write it in terms of the displacement amplitude squared, then it comes out to be 1/2 rho times V times omega S max squared. Either way you want to write it, it's the amplitude squared that determines the energy. And that's a common feature of any oscillator, including waves. The faintest sound that we were talking about before, what is its intensity? So it's just plug and chug, but we'll use the number later. The average intensity for that whisper quiet sound, it comes out to be, so I'm given the pressure, so I plug that pressure in and square it. It comes out to be 9.4 times 10 to the minus 13 watts per square meter. Roughly a trillionth of a watt per square meter. We also want to remember way back when you learned about the intensity of sound, and you learned that it obeys an inverse square law. That's the reason the fireworks sound so quiet further away you get. Because intensity at some distance from the source, or some radius from the source, let me draw a sketch, here's the explosion. You know that the further away you get at some radius r, that reduces the loudness, reduces the intensity of the sound. So the intensity at radius r is equal to the power that comes off the source divided by 4 pi r squared. Why 4 pi r squared? That is the surface area of this sphere. And so now the full energy of the explosion still is present at radius r. It's just been distributed, diluted, spread out over a sphere. And so now the concentration of the energy has been reduced by the factor of 4 pi r squared. So that's why the fireworks sound quieter the further away you get. So this is intensity measured in watts per square meter. However, usually when you talk about the volume of sound, you don't measure it in watts per square meter. Usually you measure it in decibels, named after Alexander Graham Bell. 0 decibels is going to be the quietest sound you could hear. Almost silent is 0 decibels. And then 100 decibels is going to be a loud sound. So it's a kind of rescaled version of the metric unit of intensity. It's calculated by taking number 10 and multiplying it by log base 10 of the ratio between the intensity and the reference intensity, which is that 10 to the minus 12 watts per square meter, the whisper quiet sound intensity. So that's calculating it in terms of intensity, but sometimes what you know is the pressure wave, the pressure amplitude. Now remember, intensity is like pressure squared. So if I plug in pressure squared and I take log of it, it pulls out a factor of 2. In other words, log of x squared is 2 log of x. So I can write it in terms of pressure, and then it's not 10, but a factor of 20 times log base 10 of the pressure of the sound wave, delta P max, compared to the reference pressure of the whisper quiet sound. So let me write those values. I naught is 10 to the minus 12 watts per square meter, which corresponds to a reference pressure, delta P naught, of about 2 times 10 to the minus 5 pascals. So that's how you calculate decibels. That's the volume scale that we use. For example, what's the sound level in decibels that corresponds to this intensity, like 10 to the minus 7 watts per square meter? So I need the number of decibels. It's 10 log base 10, not natural log, but log base 10. And then I have to take this intensity and I divide it by the reference intensity. You don't just take log of this. You have to divide it, compare it to the reference one, and then take the log. So I divide by 10 to the minus 12, and that gives me 2 times 10 to the 5. It's kind of helpful to just use log of A times B as log of A plus log of B, and then I get 50 plus log of 2, log base 10 of 2, which comes out to be 53 decibels. Notice it's all actually unitless. It's just that you tack on the name decibels to clarify what you're measuring. Okay, here's a nice example. A pulsating sphere creates sound waves. What's the power of the sphere, and what's the amplitude of the sound wave, and so on. So we're looking at a picture like this. Here's a pulsating sphere, and it's hitting the air around it, setting up a sound wave. The assumption we make is, and this animation does not accurately capture it, but the assumption is that if the surface moves out by plus or minus 1 millimeter, then the air around it is also fluctuating by a millimeter. In other words, we're told the amplitude of the sphere's oscillation is the same as the air. In other words, the change in radius of the sphere is equal to S max at the surface. That's the assumption that we're making. Okay, so first question is, find the intensity of the sound waves at the surface. Intensity of sound waves, this is at the surface at radius r. Of course, it gets quieter as you go out. So the intensity at the surface is 1/2 rho times v times omega S max quantity squared. And S max is just the change in radius. So let me write that. So that's just delta R. Okay, so we could predict the volume of the sound at the surface of the sphere. You have to plug in air density and the speed of sound, 343 meters per second. Okay, next, What's the power, the acoustic power radiated by the sphere? Sending out these waves, how much energy per second is coming out of it? Well, if you know the intensity at the surface, you also know the power. In fact, if you know the intensity at any sphere around this thing, you can figure out the power that's radiating out of the source. You just have to take the intensity, so this is the power, and multiply it by the surface of the sphere. In this case, it's the sphere right at the surface. It's the sphere itself, the vibrating sphere. So I'd take 4 pi r squared, multiply it by the intensity, and there you go. That would tell you how many watts are coming off this pulsating sphere. Notice it's just the inverse square law done backwards, finding the power given the intensity. Now we're at some greater distance. I'm standing out here at a distance d. Find the amplitude, pressure, and intensity. Okay. Part of the skill here is knowing which one of those things you can calculate first. The others you infer from it. Well, intensity follows an inverse square law. So I can immediately figure out the intensity at distance d. And if I know the intensity, then I can figure out the pressure and the amplitude of the sound waves. Okay, so I will find first the intensity at radius d. It follows an inverse square law. So I would take the pressure divided by 4 pi d squared. And that simplifies a little bit when I plug in the power formula I have. That comes out to be r over d, quantity squared, multiplied by the intensity I calculated in part A. That's 1/2 rho v times omega delta r squared. So notice the intensity goes like 1 over the distance squared. Okay, so there's our answer for the intensity. What about the amplitude and the pressure amplitude? Well, you see, on the other hand, the intensity is equal to delta P, 1/2 delta P max squared divided by rho v. So by knowing the intensity at distance d, I can solve for the pressure amplitude. So I'll do that, and I find that the pressure amplitude, delta P max, there's some algebra there in solving for delta P, but it comes out to be proportional to 1 over the distance. But the intensity drops like the distance squared, since the energy gets spread out over a sphere. But the pressure of the sound wave decreases like 1 over the distance, and then you can find that so does the amplitude of the sound wave. And so this is an important fact about waves. The energy of the wave drops dramatically as you go farther away. Just like the sound of the fireworks is way quieter as you go further out. The energy is almost gone, but the sound wave itself hasn't diminished as much. For example, suppose you go 100 times further away. That means the distance is increased by a factor of 100. The energy is dropped by 10,000. But the wave itself is only 100 times smaller. So the wave is still there. The energy is dropped by a lot. This is why you can, this is sound waves we're talking about, but this exact same things are true for electromagnetic waves. This is why, although your Wi-Fi router, the energy it gives off drops, the intensity from it drops a lot as you go out, the waves are still there, even if you go, farther away, or the light from the sun. The wave itself only drops like 1 over the distance.